Okay, so we're going to do limits again. So limits involve, remember, the slogan for limits, what does it look like? So limits, what should it look like? And of course, if I give you a graph, it's easy to see what it looks like. On our last homework assignment, we were working with limits left and right side, from the left and right side. What would it look like from the left side and the right side? And limits may not look the same from left and right side. So if I say this is 2, and the graph goes like this, call that 1 and 2. What's the limit? As x approaches 2 from the left side, so the f of x. And then what's the limit? As x approaches 2 from the right side. And what's the limit as x approaches 2 of the function? So we look at this problem and we say, what is the meaning of 2 negative? And we mentioned before, this is just another fancy way of saying left. And this saying right if it's a plus sign. And if there's no sign, it means from both sides. So from the left side, and looking at the graph, left side, as I approach 2, I'm not going away from 2, I'm going toward 2. That looks like it's going to be 2. Right. That's what the value looks like as I get closer to 2. But remember, the value doesn't exist at 2. Like if I write f, what is the actual value at 2? The hollow or the solid? The hollow value is not where I'm supposed to be. It's what I can get close to. The solid value, 2, is actually at 1. So the actual function value exists at when f of 2 is at 1. From the right side, we say from the right side, approaching from the right, that looks like a 1. Now, do both left and right side agree? Can we say we know what this limit looks like from the left and right? Answer is no, so we have no limit, or does not exist. Now, that's of course if you have a graph. Today, what we're going to do, we're going to look at limits just algebraically, looking at the function, and we're going to look at what specifically ones called are removable, meaning that there's a hole there. So if I draw a graph, call that 2, call that 2, what would the graph look like at 2? What's the limit? As x approaches 2 of f x, well, the left side says 1.9, 1.99, getting closer to 2. The right side, as I come down off the hill, is 2.1, 2.01. The graph looks like 2. And we're going to see that right now in our examples today. Okay, here we go. So we're going to go work through different types of questions that you might see on your multiple choice practice. So the first one is, these piecewise functions always look confusing. They always look kind of difficult to me. And the reason why is because I'm not paying attention. I'm not giving myself some time to actually read it. I'm just trying to, all math problems, trying to get it done. Now, if you look at this problem, I'm saying, let's read the first part. What's the limit as x gets closer to -3? Well, we have 2 equations. One that says, don't be at -3, and one says, hey, this is your value at -3. Now, if I wrote f of -3, where x is equal to -3, which function would I use? The top or the bottom? Okay, the top or the bottom. Which one would x be -3? That'd be the bottom, right? Because x is -3. So that means these are the conditions, and these are our functions. So the conditions tell us which function we'll be using. So the condition here is x is -3. Well, fine, use the bottom function. That means the graph is at 0. Great, 0. Now, what does limits mean? It means what should it have looked like? Well, the graph should have looked like f at -3 when I plugged in at -3 squared into the upper function. The graph should have looked like, that's -9 plus 24 minus 13. That becomes 29 minus 22, 7. The graph should look like 7. So the limit as x approaches -3 of f of x, it should look like 7. Now, we could go and graph this. And if you want to go ahead and graph this, I feel like it's kind of a waste of our time, but we could do that. If I plug in the function negative x squared, negative x squared, I think negative x squared minus 8x minus 13. What does the graph look like at negative, did I copy right? Negative 8x squared minus, negative. Oh, that's a 24, I'm sorry, this is 24. 24 minus 22 is 2. Sorry, it's 2. So when x is equal to 3, negative 3, our y value, let's see if we can get in there. Doesn't the y value look like it should be 1.9, 1.99? It should be 2, right? So the value should be 2. But our piecewise function told us, hey, everywhere but 3. So what should the graph have looked like? It should have looked like 2. What is the actual value? Based on the conditions, it's going to be negative 3. So answering the question, 2. Let's do the next problem. So these first problems are actually pretty easy. It's just working on how to read the limit. Now, remember, these piecewise functions, looking at them, the condition is this only doesn't exist at 0. So it'll look like a graph, negative 2, 1, 2, 3, negative 2 going down like that. At 0, there'll be a hole there. There'll be a hole here. And instead, we're going to graph it at negative 2. So the actual graph ends up to be like right here. So there's a hole. It's discontinuous. There's a break to it. So you can get the answers from the graph. But our goal is to not get it from the graph. Our goal is to say, hey, reading the given situation, and the situation says, hey, this graph exists everywhere except at 0, so it's going to be a hole. So what will the graph look like when x was 0? What is the limit as x approaches 0 of f of x? Well, f at 0 should be negative 2. That's what second condition said. But know what? I don't want to know what is it. I want to know what should it have been. Ignoring this now, it should have been, when I plugged in 0, negative 3. And that's what the graph looks like. It looks like it should have been negative 3. What is it in actuality? Negative 2. But it should have been negative 3. That's actually where the hole is. Okay, so these other two questions are very similar. And people freak out. They think it's something kind of weird. But the point is that these holes are forced upon the equation. So we know that if I wrote f at 3 here, well, that should have been 2. All right, that's when it's 3. Answer should be 2. F at negative 1, answer will be negative 3. And that isn't the question. The question is, what should it have been? What was the original path? And that's why we plug it into the original equation. Good. So our next type of problem is looking at fractions. And the next couple of problems will be actually fractions. The next 3 styles will be fractions, and that's what your homework will be based on. So in essence, this is like looking for the hole. Because let's go ahead and plug in 2. If I plug in 2, 2, 2, the limit as x approaches 2, what would the graph look like at 2? And if I did plug in 2, that's going to be 4 minus 12 plus 8 over 2 minus 2. That's 0 over 0. That's 12 minus 12 is 0, and 2 minus 2 is 0. This is indeterminate. That means we got to find another way. So our way of dealing with these simple polynomials is simply factoring them. And we'll see, when I factor it, we end up with x minus 2, x minus 4 over x minus 2. We had 0 over 0 here. Why do we have a 0? Because we had an x minus 2 in both of them. And when I plug in the value 2, it made each of these become 0. Well, let's divide them. They go away. And we're left with the limit. Sorry, you have to write limit here. You always have to keep writing limit until you plug it in. The limit as x approaches 2 of x minus 4. Now that we got rid of our offending 0 over 0, we can now replug it back in. 2 minus 4. Notice I don't write limit anymore. There's no limit. It's gone. See, no limit. Limit. Whoops. I don't write limit anymore. After I plug it in, I don't write limit. Is equal to -2. That's the answer. That's what the graph should have looked like, because that's the whole. That's what the whole looks like. Our next problem, similar. Let's go ahead and plug in -1. -1 squared is 1 plus 1 minus 2 over -1 plus 1. This is just a check. Oftentimes for limits, go ahead and plug in the value, see what that looks like. Maybe we won't have a problem. But in these types of problems, since we wrote them the way we did, we know we're going to end up with 0 with 0. Darn it, 0, 0, find another way. It's indeterminate. Indeterminate. Okay. Let's go ahead and factor it. It's going to be x. 2 and 1 make 2. 2 minus 1 is 1. You have 2 and a 1. More negatives than positives. Limit as x approaches -1. Hey, you guys see a common factor? We do. And that was my 0. That was my 0. We're left with the limit as x approaches -1 of x minus 2. We plug in -1. Oops. -1 minus 2. Again, if you look at what I did here, I do not write limit after I plug in the value. But you have to write it you have to write the limit until you plug in that value. And that answers -3. Okay, so practice factoring. First, plug it in to check if you get lucky. If you don't get lucky, factor and replug it back in. So now we're looking at problems. Once again, this one doesn't look like a polynomial. It's a fraction. A fraction over a fraction. I oftentimes call this a tower of terror. But we have a method of getting rid of these fractions. So here's what we're going to do. Try plugging in 0 first. If I plug in 0, we end up with 1 over 1 plus 0 minus 1 over 0, which is 1 minus 1 over 0, which is 0 over 0, which we know is indeterminate. We have to find another way. Now this is actually an algebra 2 move. And hopefully you guys remember how to do this. If you multiply everyone by the common denominator. In this case, the common denominator will be x, 1 plus x. Let's look at our next problem before we finish. This one's the same thing. Common denominator, multiplying everyone by 1 plus x. This problem here, common denominator is going to be, 2 and a 2 plus x. So we have 2 common denominators. Over here, negative x, 1 plus x, negative 1 plus x. Okay? So be aware that the common denominator could change, but that's what we're multiplying by. So the common denominator multiplies to the front and the back and the bottom, okay? We'll multiply everyone by the common denominator. So why do we do this? Because it gets rid of the fraction. So let's go ahead and rewrite it a little nicer. Multiply to the front and to the back. When I do that, we end up with a 1 minus 1 plus x. Okay, how do we do that? Because 1 plus x times 1 over 1 plus x, the fraction divides out. That's why we do it. And we're left with just a 1. And negative 1 times 1 plus x is a negative 1 plus x. the bottom becomes x, 1 plus x. If we go ahead and plug in 0 now, we would still end up 0 over 0. Oops, limit. So we're going to simplify the fraction. 1 minus x over x, I'll leave it, x, 1 plus x. The top, look here, those get rid of each other. Whoops. So our limit, as x gets closer to 0, of negative x over x, 1 plus x. Do not multiply these out. Okay, do not multiply those out. It'll save you time in the long run. The x's divide out, as you can see, that was my offending 0 over 0. Just like what we did before, you get rid of that 0 over 0. And then we end up with limit, as x gets closer to 0, of negative 1 over 1 plus x. And now we can plug in our 0, and we won't end up with 0 over 0. Negative 1 over 1 plus 0 is equal to negative 1 over 1, which is negative 1. So there are a couple skills to solving for limits, and it's not that they're hard. You just have to practice and know which tool to use for which case. Let's look at the next problem. Very similar. So our next problem, we're going to multiply by the common denominator, which is going to be 1 plus x, 1 plus x. And we do that, limit, as x approaches negative 1, of x, 1 plus x. Now the hint is, do not multiply those out, leave them alone. Divided by, we're going to distribute the 1 plus x to the front fraction and the back. So the fraction goes away, we're left with 1 minus 1 plus x. We're going to simplify the denominator because we're going to look for that 1 plus x here. So we're going to be left with limit, x approaches negative 1, of x, 1 plus x, over, distributing it will be 1 minus x, distributing that negative sign. And we see the 1's subtract from each other. We're left with the limit, as x approaches negative 1, of x, 1 plus x, all over negative x. We can divide our x's. X limit, as x approaches negative 1, of negative 1 plus x, plugging in negative 1 in, and we're left with negative 0, which is 0. Now, why did I have to do that? Is because if you look here, and if we plug in our negative 1, I forgot to do that right at the beginning. Look what happens right here, 1 minus 1. Does that give us an answer that makes sense? No, we end up dividing by infinity. And we can try to do this problem over again, and it turns out it's going to look like 0. This one here, I'll just tell you guys what my common denominator is. It's going to be 2 plus x, and 2 plus x. And the reason why I'm doing this, because I want to get rid of the whole fraction. And from algebra 2, you practice that. And as I set this up, limit, as x goes to 0, of 2x, 2 plus x, over, when I multiply this to the front and to the back, we end up with the 2 plus x dividing out, and we're left with just a 2 times 1 is just 2, minus the 2 divides out, 2 plus x. Okay? And as you simplify that, do not multiply that out. Just finish this up. 2 minus x, those go away. And then we can simplify from there. Okay, our last skill today is going to be radicals. And we had practiced this before. It's about multiplying by the conjugate. And the conjugate, let's go and take a look at what that looks like. So the conjugate here would be the square root of x plus 6 plus 3. That's the conjugate. X plus 6 plus 3. Now, why do we have to do this? Well, like normal, you should plug in the x, and then if I plug in 3 here, 3 plus 6 is 9. The square root of 9 is 3. 3 minus 3 is 0. And on the bottom denominator, 3 minus 3 is 0. We end up with 0 over 0 again. 0, 0. Oh, my friend. So the rule here is to multiply by the conjugate. So we multiply by the conjugate. A couple things. I'm going to show you guys one of the tricks that you should remember from Algebra 1. If I say x plus 2 and x minus 2, since we know that middle terms are going to be opposite signs, we can just write x squared minus 4. So for square roots, in a very similar fashion, square root of x plus 2, square root of x minus 2, we end up with a 2 square root of x in the middle. See, the middle terms are always going to be opposite signs. So forget about it. Just do the front and the back. Because square root of x times square root of x is just x, cleans up. And 2 times 2 is 4. Now we can do the same process for this question here. If I multiply the square root and square root on top, that's just x plus 6 minus 9. That's in one move. 3 times 3 is 9. Negative 3 times the positive 3 is a negative 9. On the bottom, we're going to leave it. Please leave it alone. X plus 6 plus 3. We're going to simplify the top. Turns out that's x minus 3. Check this out. Does this look familiar? And that's my 0. Oops, I forgot to write the limit. If you don't write the limit, it's wrong, okay? So once we see that, we can divide those out. And we're left with the limit as x goes closer to 3 of 1 over the square root of x plus 6 plus 3. Now, since we got rid of our 0 over 0, plug in our new value 3. 1 over square root of 3 plus 6 plus 3, which is 1 over square root of 9 plus 3, because 3 plus 6 is 9. And that's really equal to 1 over 3 plus 3 equals 1 over 6. Okay, so the same process is going to happen for all these square roots. And as we look at these different problems, they all have a conjugate. We multiply by a conjugate. I've included the answers for your practice. Just the first one. Oh, actually, you know what? I don't have this practice. I have another one for you guys. You guys have your multiple choice to work on today. Where did the x plus minus 3 come from? X minus 3 came from right here. 6 minus 9 is negative 3. So we're left with x minus 3. And that's the factor I was looking for to divide out from the bottom. Yes, I just simplified it so that the numbers will be super obvious. Yep. Okay, do you guys need me to do one more example of this, or we're okay? Let me know. One more? Sure. Let's do one more. Okay, let's do the fraction on the bottom. Sure. Okay. So if I plugged in 2, if I plugged in 2 on top, that's a, whoops, plug in 2 on top, that would have been 0. I plug in 2, 2 minus 1 is 1, square root of 1 is 1 minus 1 is 0. We have another 0 over 0. So we're going to multiply by the conjugate. Conjugate's going to be x minus 1 plus 1. The sign change happens between the two terms, not inside the square root. Top, square root of x minus 1 plus 1. Right? We're just really, that's just 1. So we're doing us a favor. And the reason I'm doing this, I'm trying to get rid of that radical from the denominator or numerator. Just to get rid of it. Mix it up a little bit. The cool thing is that we've worked with this pattern before. So it's just going to be square root of x minus, whoops, sorry. So a square root times a square root goes away. So it'll be x minus 1 minus 1. How did I do that so quickly? The square root becomes x minus 1. There's no middle term. So we just multiply the backside. Negative 1 times 1 is negative 1. Normally when you have two problems, x plus 2 and x plus 2, see how they're both the same sign? You have to do the front by the front, front by the back, x squared plus 2x, and the back by the back, back by the back, plus 2x plus 4. And you end up with terms that are exactly the same. But if I flip a sign from plus to minus, one of these change, and they always go away. So the conjugates are great. The top, do not multiply it, leave it as you see it. Leave it as you see it. Limit. Now when I simplify the denominator, x minus 1 is x minus 2, which is what we were looking for. Great. The limit, as x approaches 2, we only have the square root of x minus 1 plus 1 over 1. And we don't really have to write the 1 on the bottom. How do we get the 1? Is because those two divided out. And it's cleaned up. Now that we're clean, we can go ahead and plug in our 2. X becomes 2. Equals to the square root of 2 minus 1 plus 1. 2 minus 1 is 1. And that's going to be 2. Yay! Okay. Hopefully you found that helpful. Do you guys need me to do one more? Or are we kind of singing it now? Okay, I'm going to stop the video. Sure. Okay, let's do one more. Okay, so if I plug in the 2, 2 minus 1 is 1, square root of 1 is 1, 1 minus 1 is 0, and 2 minus 2 is 0. All right, we know this is going to be 0 over 0. It's indeterminate. So our goal is to try to mix it up. And we're going to do that by multiplying by the conjugate. Oops. Okay, and is that the conjugate? Nope. Got to change it to a plus. We do not change the stuff inside. The reason why we do not change the stuff inside, because if you multiply them and they're different, the square roots don't go away. They're totally different numbers. So they have to be the same radical for us to clean up nicely. Okay, that's the logic behind it. So when we multiply the top, since it's a square root times a square root, that's going to be clean. Since it's a conjugate, we have no middle term, so we just do the back term. On the bottom, we're going to copy the problem, leave space, do not multiply this out, because we know it's going to simplify. Look at the top, -1 minus 1 is going to be a -2. Hey, that's the same term here. You're going to get to simplify it and divide that out. Oh, darn it, I forgot to write limit. So it's a limit as x is closer to 2. Since we can divide that out, whoops, ugly. Divide that out, we're left with 1 on top over square root of x minus 1 plus 1. Simplifying that, we're going to plug in our 2. 1 over square root of 2 minus 1 plus 1. 1 over square root of 1 plus 1 is 1 over 2.